Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I have a big pleasure of introducing Professor Peter Leach to you this afternoon, to you in this room and to you online. Yeah, so good afternoon to everyone. Professor Leach did his PhD in Australia and has also a DSc degree from the University of KwaZulu-Natal, where he's currently Professor Emeritus, and he's also honorary research fellow at the Durban University of Technology at the moment, but had many other famous appointments in between. He's one of the most prolific applied mathematicians that I know, with over 350 papers, so well done for that. And he's also a very highly cited mathematician. And this afternoon is here to share with us a little bit of his wisdom on what every mathematician and theoretical physicist should know, yeah, and probably doesn't. Yeah. So, Professor Leach, thank you very much for being with us this afternoon, and the board is all yours. Thank you.
Thank you, Francesco. Just let me lean over on this for a while. It's very nice of you to come along, and you're probably wondering why the strange title. Or you're not wondering. Well, it's very simple. It's why do we do things? Why bother? Now, I think there are a couple of explanations. First of all, you really need to divide the human population into two classes: those who bother and those who don't bother. Now, I'm not going to talk about the people who don't bother because I can't be bothered talking about them. Now, if you think about it, why are you here? I'm not talking about in the auditorium. That's because you wanted to come and have a glass of sherry afterwards, or whatever. You're here as scientists. Now, you're looking at things. You want to look at things. And why do you want to look? To find out what's going on. And so, if you go and look at any area of activity, the sort of activity that people like us get involved with, the question is, I don't know, do you ever come across Julius Sumner Miller? No one? He was an American who produced a TV series called Why Is It So? Right, you remember. You don't? Well, maybe it didn't penetrate Africa. It was a long time ago. And anyway, the series was, as I said, Why Is It So? And that was his constant refrain. Why is it so? Well, the question one should ask initially is, why do you ask that question? Which I know is a little bit semantically inept, the most polite thing you could say. But it is a matter of saying, I am interested to know why. And out of that comes all sorts of possibilities. The possibility that you can actually come across something, some method of understanding the reason. Now, I personally, well, first of all, you've had a potted history of the sort of the second half of my life. I think I ended up here very much by accident. Not just one accident, a whole series of accidents. And I'm not going to bore you with all of them because some of them are quite personal. But it really is something of an accident. When I started off working, I worked as a high school teacher up in some dorp in the country, and it was a very enjoyable life. We had the best golf course in the country just across the river on beautiful sand country. I don't know if any of you play golf, but this was, nice sand dune country. Right, I'm getting one knowledgeable nod. And it was actually hard to leave that place, but I had to because of family circumstances. And I thought, I need to get a job. So I went to the equivalent in Australia of the technicons. I don't know, do we still have technicons? Or have they all become universities now? Right, well, there used to be technicons. And this place was the equivalent of one of them. And in fact, it was probably gone exactly the same route of starting off with matters technical, just going up, becoming a bit more complicated, looking at wider things which are not normally associated with a technical college. And then, as it seems that with a lot of everything, it has to become a university. Well, we don't have to go very far to see an instance of that. Well, actually, I don't have to go very far because it's in Durban. We used to have the Durban Institute of Technology, but of course now it's no longer the Institute of Technology, it's the Durban University of Technology. And I must say, as an educational institution, it's quite good. I don't know what it's like with the technical matters, of course, because I'm not a technically inclined person. Anyway, the question is, why bother? And I think I can truthfully say, well, I can truthfully say for myself, I don't know about anyone else, it's because of accidents. Now, yes, one or two of you are old enough to remember the 50s. Not many, I know. You remember in the early 50s, well, you won't remember, but I'll tell you, there was a great interest in the hydrogen bomb because the atomic bomb has been shown to be quite effective. So let's make it bigger and better and boomier with a hydrogen bomb. Now, there were some people who were a bit upset by this. They had perhaps visited various parts of the world where conventional bombs had been dropped and done enough damage. And then the idea of a hydrogen bomb was a bit devastating. So they thought, no, wait a moment. We know the whole idea behind the hydrogen bomb is to persuade a couple of hydrogen atoms, probably deuterium or tritium, but they're just isotopes really, to combine together to give you helium and scads of energy. Now, if you could do this in a controlled way, you would have energy available not indefinitely, that nothing is indefinite, but you could solve the energy problem for a long time. Because if you look at the statistics these days, with the usage of coal and oil, people are running around looking for these things all over the place and going to the most remote locations because all the stuff that's easy to get is gone. It's been used up. So there was this pressure, you might say, to control the fusion process to go and prolong mankind's existence for another 1,000 or so years. So at the place where they developed the atomic and hydrogen bombs, which is in Los Alamos in New Mexico, they set up a division there to look for controlled thermonuclear fusion. Now, the whole idea behind this was actually based on some mathematics or physics. You can take your pick depending upon which side of the fence you are. On the motion of a charged particle in a magnetic field. But the difference would be here that the magnetic field would not be constant, but would be rapidly varying. And the question is, how on earth can you solve that problem of the motion of a particle in a magnetic field which isn't constant? Well, Lorentz came up with an idea around about 1880, so you can see it was a problem which was occurring to them, but it arose actually as what you might call a toy problem. You think of a pendulum, a bit of metal on the end of a string, and it's held by a clamp. Now, normally you screw the clamp up so the string just hangs, then you move it and it wobbles around like that. But now, what happens if you don't tighten the clamp enough? The weight of the bob would slowly draw the string in through the clamp. And in fact, it could perhaps be moving faster, but the toy problem was set up for a slowly moving bob falling down. Now, you think the thing's makes a pendulum, and you make the usual approximation for a pendulum, where you have small amplitudes, and so it just becomes a harmonic oscillator. Now, if the length of the string is constant, it's definitely a simple harmonic oscillator. But if it's not, then it's not a simple harmonic oscillator, because that change in the length means a change in the omega squared of the oscillator equation. Sorry, that'd be the oscillator Hamiltonian. What do you do then? Well, let's just say Lorentz came up with this idea of what was called an adiabatic invariant. It was adiabatic because this was all done in a slow motion process. Now, all right, that's a toy experiment. I mean, if you're going to have a pendulum where the string is slipping, why don't you just go and call the technician to make it tighter so it doesn't slip? That solves the problem. It does. Okay? That's why we have technicians. They can solve these practical problems. But if you're dealing with a situation where it isn't a process of just tightening a clamp, because you've got this huge experiment going on, huge magnets and things doing rapidly oscillating electric fields or electromagnetic fields, it's another matter. Anyway, but the thing was, the same equation arose. Well, it was handy because they say, oh, well, Lorentz worked out an adiabatic invariant for it some time ago. We can use that. But then someone says, yeah, well, the trouble is, it's varying very rapidly. And then you have a real problem because, you know, if you think of it, suppose you have your pendulum like this, and you pull this wobbling backwards and forwards, and you pull the string up through the clamp, what's going to happen? You haven't done it. You just let them fall through. As you pull it up, it's going to, right? Someone's done the experiment. It's then a problem that this whole idea of Lorentz just doesn't work. But there we're getting up more into the realm of the charged particle moving in an electromagnetic field. And of course, as I was saying, the people at Los Alamos, and probably someplace in Siberia, were very much interested in this type of problem. So, what is one going to do? Well, you can invent a method for getting a series expansion. Just keep making further and further and further approximations. Now, to do that, first of all, you need to be a very diligent calculator. And secondly, you have to be lucky and persistent and have a mind which can take in some quite complicated problems in terms of the actual calculations. Well, a friend of mine at Los Alamos, he did this. Curiously enough, he was in Germany, in Heidelberg, on sabbatical when he did it. And I remember him telling me the story about being high above the Rhine River, and he's working away this calculation and calculation, and eventually he came up with an answer, because every time he did this perturbation, the same expression kept coming up. And he thought, well, probably it was a bit louder than that. And he realized that he had the answer to the problem. All you had to do was to work very, very hard. Well, because of this particular problem, which I've become interested, I had contact with Ralph, and after I'd struggled through these awful papers, I said, there must be a simpler way of doing it. You see, this is the difference between a mathematician and a physicist. The mathematician looks for the easy way out. The physicist looks for the right way out. Is that sufficiently politically correct? Anyway, I came up with a very simple solution. If you write down the Hamiltonian for this problem, you can then think of the whole process of using transformations, canonical transformations in Hamiltonian mechanics, and with a little bit of effort, you can go from a time-dependent Hamiltonian to a time-independent Hamiltonian. We're still talking about the oscillator, remember? And you can actually write down the Hamiltonian as just as a half of p squared plus q squared. Now, anyone can solve that. Well, anyone who's done Hamiltonian mechanics, I mean. So, we had that, and a very simple way to get it, something which people could follow and do it in a finite time. But this whole idea of using canonical transformations to simplify time-dependent problems was then spread into quite a large number of problems which had arisen in physics. And so it was really a very successful little calculation. Well, at least it got me to go skiing in the mountains near Los Alamos. So it did have its benefits. You don't go skiing, do you? No. I used to do it quite enthusiastically. You know, in Australia, they do have mountains with snow on them. So that started me off. I went to Los Alamos a few times, did some more work. And there I met someone from Belgium. And slowly my interests over the decades have moved from the States to Belgium, France, then Italy, then Greece, and Cyprus, and then with a big jump all the way across to India. It seems that the Indians are still interested in what I do. Now, one of the things which came out of the study of these exact invariants, as they like to call them, or these Hamiltonian systems, and of course their associated differential equations, was the fact, again, going back a long time, back to the 1880s, when the Norwegian Sophus Lie started doing his tricks with transformations. Now, his idea was to use infinitesimal transformations. Now, you're familiar with the idea, for example, if you have a sphere, you rotate it by an angle, and it's still the same sphere. But you're thinking in terms of a finite transformation. Well, Lie cut out the complicated parts by just using infinitesimal, because when you use infinitesimals, anything smaller than infinitesimal, you just ignore, and it works fine. Well, he applied these two differential equations, and he found that some equations had these transformations which left them invariant. So if you have something and you transform it, and it's still the same, you say it has a symmetry. A very simple example of that, for example, if you take a disk and you rotate it about the center, it still looks the same. So it is invariant under rotation, and you can write that rotation in an infinitesimal form, and there you have something very simple. What if you have a three-dimensional object? Take a sphere. Now you have more opportunities for rotation. In fact, you have three opportunities, and you rotate the sphere according to any of these possibilities or some combination of them. You still end up with the same sphere. And You get the differential operators for it, and they're well known, of course, to be the rotation group. You know all about rotation groups, don't you? Good. Someone, oh, I know you do. If you listen, if you have to ask a question, please jump up and down and wake me up, because I may be saying something which is not easy for you to follow. Now, if it's not easy for you to follow, it's possible that there are one or two others in the audience who are having the same problem, but who are too shy to speak up. So if you want to find out, ask. I trust you get the message. I didn't see any heads fall off, which means not much enthusiastic nodding. I resist the temptation to make any nasty comment. I am. Actually, I saw someone walking along before. This is not an exceptional example. They've got their, what are these things called? Cell phones, is it? Right, he's got his cell phone like this and walking along. I'm going to look where I'm going. I don't know how they do it. No, honestly, I don't. And once more, they can manage to walk in a straight line, except when you have to divert to avoid a, shall we say, an unnecessary encounter. Right, I wanted off the point for some reason, sorry. Anyway, we're talking about these rotations, and you have the rotation group. And the rotation group can be written down in terms of differential operators. You get three of them. Now, what happens if you combine two of these rotations? Well, it's a question. I'm sure there are enough people to answer it. So, right, you get a new rotation. So the composition of two rotations will give you a rotation. Each rotation can be thought of in terms of asymmetry. So if you can combine the two rotations to get a rotation, presumably you can combine two differential operators, which each one corresponds to symmetry, to a rotation. You can combine them in such a way as to get another infinitesimal operator, which will give you the composition of the two rotations. Now the question is, how do you combine the two infinitesimal operators? Must be a very good question. Now, say you had rotation like that, then a rotation like that. How are you going to combine the two? Well, I gather there are no Norwegians here. Right? You don't know. Oh. I told you so. Well, let's stick with just one of them and call it a different name. Although we'll be fair to you and say we can call it the commutator. But in this particular instance, it's usually called a Lie bracket, named after Cephas Lie, who invented it all. So you combine the two transformations, you get a transformation, and all of that is reflected through the commutator of the operators generating the transformations to give you the resulting transformation. Now, it's easy to visualize this in 3 dimensions. It's probably easy to do it in 2 dimensions, but it's a little bit boring that way. 3 dimensions, you do get a bit of excitement. And because you can visualize the transformation occurring, it's easy to go and understand the way the differential operators work. So you think about that. And then, skipping a bit of detail, you start realizing that you can analyze differential equations. Actually, you can analyze other things as well, but I'll just stick to differential equations for their symmetries. And for their symmetries, you can calculate the set of commutation relations, and from that, you know the algebra. Now, the thing about algebras, because there are lots of them, is that they can come in different forms, different expressions, depending upon the circumstance. And you could say, well, look, that's like that, and there's no connection. Then someone comes along and says, oh, wait a moment, that has a 3-element algebra of a certain type. That has a 3-element algebra of the same type. Therefore, they're the same equation, just written differently. So that is actually one of the important features of these things, that you get different representations of these algebras. But then you get different algebras which are not going to be representations of the same thing. And so you have this one has an algebra, that one has an algebra, and they're not the same. Well, you might say, okay, that was sweet. We can now solve the not so simple harmonic oscillator. But then what happens? You actually stop thinking about the physics involved and concentrate on the differential equation. Now, differential equations pop up all over the place. All you have to do is have something varying in time, preferably in a nice fashion. We don't want too many jumps all over the place. You can still analyze the equation. And in analyzing the equation, you can say, right, it has that symmetry, algebra, sorry. Now, from that algebra, which is, remember, is made up of differential operators, you can then no, I don't know what the term is. Do you use the term exponentiate? You're the spokesman. Oh, that was a nod. Okay, so everyone knows what exponentiate means. Personally, I don't. But you can find the finite transformation connected with the infinitesimal transformation. Now, that technique has actually been around for several centuries. Well, at least a century and a half. No, it must be nearly 2 centuries now. Because it goes back to the days of Laplace. Yes, that's a fair while ago. And it's quite simple in principle. Now, bear in mind, I'm talking about in principle in most cases, because in actual practice, you could end up with something highly complicated. And that's one of the unfortunate facts of life. But one can only try. Now, one of the things, as I just mentioned before, is that differential equations have this habit of popping up all over. And for example, if you look at economics, you find that there are differential equations arising in economics. Now, once you forget what the symbols mean and just look at the equation, they could have arisen in mechanics or fluid mechanics. So you can then go and study the equation for its symmetries, and you may even be interested in the algebra. I'm not too sure that people who delve in finance are very much interested in algebra, but you can take the operators, infinitesimal, remember, and find the finite transformations they represent, and so perhaps take a very complicated looking equation from economics and see that in fact it's really quite a simple one. The simplest partial differential equation that I can think of, and talking about second order generally, would be day 2u dx squared. Do you use day or dou or what? When you're speaking about a partial derivative, you don't do partial derivatives? Come on, someone must know. What symbol do you use when you're writing down the partial derivative? Right, what do you call it? Oh, you mean partial u, partial t? Oh, great. Well, I've learned something. I did not know that that was one of the usages. No, you probably do it all the time. I realize that. I all the time have done something else. Huh? No, it's not delta. Delta is something else. Delta is for that little thing that you, yes, for which you say that got a small change, whereas that represents more of an infinitesimal, not a small. Right. Okay. So you're happy with partial. It's a wonder someone didn't jump up and down before and say, well, what are you talking about all these days? No. No comment was the stern reply. All right. Now I've lost track of what I was telling you about. I have completely. Yes. Right. I think we were talking about economics, weren't we? For example, have you heard of the Black-Scholes equation? You have. Right. You have? You haven't? You mean you've had your one moment of success and that'll be enough for the day? Right. Black-Scholes equation is an equation from economics. Once upon a time, economics was just what you might call a talky subject. People would sort of say, well, there are these influences and those influences, and this will lead to that and that to that, but it was not a quantified subject. But problems in economics do become more complicated as time goes by. And one of the things was that it became necessary to express things in terms of derivatives. Now, I'm talking about our derivatives, not the derivatives that the financial people deal with. And so you then have an equation. And what do you do with an equation? Well, what's the prime purpose of an equation? Sorry? I didn't hear you. Didn't understand. What? The price of options. Is that what it is? Yeah. Well, you see, that's what comes with being a poor academic. You don't know these things. Obviously, being a professor of physics is different. So, oh yes, the options, of course, became big business because people wanted to make money. And why did they want to make money? You know, there was an item on the news the other day that the stock price of the New York Stock Exchange had gone up by 1 or 2%. And this poor fellow, his net worth had increased by $400 million. So I guess he knew how to play the options. It's a bit hard to contemplate $400 million. The four I can contemplate, it's all those zeros after it that sort of don't help. Now, of course, it was a drop in the ocean for him anyway, because his fortune was estimated to be several $1 trillion. I didn't even know they used trillions for dollars. But so you learn something just by reading the news and by saying, I wonder if he was using the Black-Scholes equation or maybe some more sophisticated variation. Why would you want a more sophisticated variation? Now, you have to speak up, my dear, because there are some deaf people up the back. Refined. Oh, yeah, precise. Okay. Right. Well, here you are. You can now go and speak to this very nice young man. Ah, good grief. Do my best. Right. You want to have a more refined model so that you can tweak it before it tweaks you. No, it's serious. Well, look. Now, suppose you were like this man in New York, and you've just made $400 billion because something went up for you. What would happen if it had gone down by that much? It'd be 400 billion or off. Of course, in several trillion, you may not notice a few hundred billion, but that's another story. So the point is you need to be as precise as possible and to make your models as accurate as possible so that you can be accurate. Now, of course, when I say accurate, I'm not talking about 100% accuracy. It'd be nice if you could, but there's always a degree of approximation. Now, why is that so? All right. Does anyone know what affects the, was it Dow Jones index, isn't it? You know what affects that, whether it goes up, down, or runs around the corner? Sorry? Well, it actually could be true, you know. Did you hear that up the back? Butterflies. Well, if you can get them in your stomach, I suppose they can do other things as well. So the problem there is you want to be precise. Is that the word? Right. And you know you can't be 100% precise, but you want to be as close to 100% as possible. Well, as we were saying, you take all the possible influences that you can into account. Now, that requires a good understanding of finance in this particular case. And it would be almost impossible, I would say. I'm not saying 100% impossible. Almost impossible to identify all the possible influences on the value of the Dow Jones index. The same thing applies for JSA, but JSE, sorry. I had to spell it. And in fact, you might say, well, some places would be more stable than others. This is quite possibly correct. And that stability, of course, can vary in time. For example, I guess none of you remember 1929 very well. One's smiling at the memory, so you didn't have any shares at the time. Yes. Now, the reasons, which I must admit I don't understand, the value of the stock exchange in New York just went boom, which is quite a considerable drop. What happened? You see, you're just far too modern, aren't you? You ever heard of the Great Depression? Right. Well, that triggered off the Great Depression because confidence was lost, markets collapsed, investors jumped out of windows of 20-story buildings, and a lot of people ended up unemployed because companies were just going up the wall or down the drain, whichever you prefer. And that was just because of one place in the world. It was a very dominant place, but it still was just one place, but the effect spread in a quite widespread way to Asia, Africa, rest of Europe. And there were consequences of that. I thought someone would offer a suggestion as to one of the worst consequences. You're getting close. A bit before World War II, you had Germany was, shall we say, very unhappy. And so it allowed a person like Adolf Hitler to just rise to power and then cause World War II. Huh? Oh, shoot. Oh. Although there is someone who's made the argument that World War II was actually really World War One Part Two. Oh, okay. I've got a man who nods his head without snoring. Right. Francesca? Oh, okay. I've no idea. I haven't had a watch for at least 30 years. There's a good reason for it. I had one and I lost it. Well, if you're going to lose a very sentimental watch, you can't replace it. So it's best not to have one and just wander around in a state of vague confusion. And I do that very well. Right. Well, that's about enough of economics. They call it a dismal subject. I think I know why. We've had some physics. We have these mathematicians lurking in the background trying to make a penny out of everything by inventing all these things. What about in biology? I remember it's quite a few years ago, there was a funny show on the radio, and someone said that, he didn't say what about biology, he said what about something, which I've forgotten. And the other person in this comedy says, yes, indeed, what about it? Oh dear. This is really quite depressing. Sorry? Oh, that's true, you do. Yes. Well, maybe we should do geology. Well, we'll think about that. You start thinking of models of biology. Now, remember, biology, that's including botany and zoology and maybe some other ologies that I can't think of, is concerned with the properties of living things. And you might say, well, what do differential equations have to do with that? But then along come these people who know a little bit of mathematics, and they start saying, well, let x be the unknown. You remember that from your first book on algebra? You didn't have a first book on algebra. Well, that was about 70 years ago in my case, and I can still remember the introductory thing in algebra was that let x be the unknown. And then you do things about it. You sort of multiply by 5 and add 3 and say that you actually ended up getting 8. What is x? It's true. Oh, good, you agree with me. And of course, you did some little operations and you came up with a complicated answer like x equals. Don't tell me you haven't done it. I made a simple example for you. Thank you. Now, algebra sort of evolved a lot from that level of simplicity. Well, first of all, you ended up with quadratic equations. And heaven forfend if you got up to anything higher. But algebra also moved in a different direction where you started thinking in terms of operators and, as I mentioned some time back, of rotations, for example, which the finite rotations form a group. And if you take the infinitesimal version of the rotations, you get these differential operators, 3 in number. Take the commutator or Lie bracket, and you have an algebra. And wherever you find that algebra, doesn't matter what the representation is, you know it's related to the rotations that are possible. And that's that. So basically what you could say is that once you start on something, a useful idea for a particular context, it can evolve into being a much more useful object to the extent of its wide applicability. And that there is where a tale ends.
Thank you very much for a very nice tale. Any questions for Professor Leach?
I've got a suggestion. No sherry for those who don't have questions.
That is okay. I think that here comes the question. The only one who will get drunk this evening.
No, I didn't say get drunk.
You told us about your. Can you hear me? You told us about your first result.
Yes.
What do you consider as your most significant result, if there is one that can be isolated?
That is a very good question. And I'm actually almost inclined to say it was my first result, because everything else grew from that. Now, fortunately, I was helped by others who taught me about the algebras and things like that. But it was perhaps the conservative nature I have, that you have something which is invariant, even though the physical system is jumping around like nobody's business. I think that would be.
Thank you.
Any further questions? Then maybe I ask you one. You told us a very nice history. How do you see it evolving? What can we expect in the near future?
That's a very good question. And I think I can give you a very brief answer. I don't know.
That's very fair.
Look, I'll try to be slightly less facetious. We have seen that the idea of invariance based on symmetry, which is a necessity, has been expanding and expanding and expanding into different fields. Now, if there are still fields left untouched, there is the route for expansion. And of course, bear in mind, the source of new employment for those who know what's what. Of course, it does require a bit of effort. I mean, if you're going to model something, and we'll take your butterflies if you like, but I'll bring them back to you, don't worry. If you wanted to model the lifestyle or behavior of a butterfly, it could be quite complicated. Now, the other day, I was sitting out on our stoop, You know, oh, wait a minute, I'm in South Africa, aren't I? Sorry. And there were these birds. It was around about 5, so the day was drawing to a close. And there's this whole lot of birds, a good 200 of them, just carrying around. Why were they doing it? I don't expect you to say that you know, but there is a question. One which is just sitting there, that you sort of wait till the appointed hour, and then you say, well, why do they do that? Why don't they just go home and go to bed like any sensible person? Apart from the fact they're birds, not persons. Ah, that's the answer. They're bird brains. I do try.
Do we have any questions from the people online?
Hi, no, just people asking where they can find the presentation online afterwards. So on the YouTube, yeah.
We will sort it out later. Okay, then Peter, we have a little gift for you. And I would like to ask Sophie to give it to you because she's responsible for the creation of the gift. And maybe you can tell Peter Leach what you're going to give him just now as a little thank you for his talk. For putting me on the spot.
It's a mathematics magazine about the stigma around mathematics. Okay.
Oh, breaking the stigma around mathematics, that's terrible. No. I'll just hide the title.
Very much again.